So throughout this talk, K is always an algebraically closed field. Oh, use this. And it's not always needed, but I'll assume it for simplicity. When I talk about a form, I always mean a homogeneous polynomial of positive degree. And R will always be a polynomial ring over the field. And I'm going to call the number of variables capital N, and I used a very big letter because I want you to think about the case where the number of variables is very large and you can't control it. You have no idea how many variables you have. And so I want to remind you that a free R module is just basically a direct sum of copies of R, and it could be infinite. The polynomial ring itself is a direct sum of infinitely many copies of the field, for example. But when you have a finite number of copies, the module is just basically this finite direct sum. And it's the same as the product of H copies of R. Now, if you're given vectors in this free R module, you can worry about the relations on them. What are the, you can multiply by elements of R and use them as coefficients and look for relations just as you would with vectors over a field. Here, we're talking about modules all the time, but they're like vector spaces. It's just that the coefficients are restricted to a ring. And by the way, this talk is designed for a general audience of mathematicians, although I suppose there are maybe a lot of commutative algebraists, but it is intended to be comprehensible to people who haven't studied commutative algebra. So I apologize to the commutative algebraists. They'll sing a lot of stuff they know. So one can talk about relations or syzygies. Those are synonymous. So they're given, if you have m vectors, to give a relation, you need to give m coefficients, f1 through fm, and they form a vector in Rm. And you want to use these coefficients on the vectors and get the sum to turn out to be 0. So you're interested in finding a finite set of generators for all the relations. There are always infinitely many. You could take any relation and multiply it by anything you like and get lots more. And you can add relations. So they themselves are a module. But you just want to get generators for them to understand them. And those generators are a new sequence of vectors, although your original vectors may have been in RH. If there are m of them, then the new vectors will be in Rm. And here's an example. If you start out with the variables, which are in R1, and you look for the relations in this polynomial ring, they're spanned by 3 vectors. One of them is 0 minus x3, x2. That gives a relation on the 3 variables. And another one is x3, 0 minus x1. And the third one is minus x2, x1, 0. So if you want to see the first relation in action, those entries of V1 have become the coefficients on the 3 variables. And now when you look at the 3 vectors, V1, V2, V3, they're not independent. They have one relation themselves, namely x1, x2, x3, because this linear combination of them is 0. So the first module of syzygies is spanned by V1, V2, and V3. And the second module of syzygies is spanned by just the vector x1, x2, x3. And there are no relations. So after this, the modules of syzygies are 0, and the process stopped. Another example, you can consider the size 2 minors of this matrix. We're working in the polynomial ring in 6 variables. The variables are the entries of the matrix. And I'm going to call the 3 2 by 2 minors delta 1, delta 2, and delta 3. And there they are. And it turns out they have two relations. So one relation is given by the first row of the matrix. In fact, if you duplicate that row and expand by minors, the determinant is 0, and that gives you the relation. And the other relation is given by the second row, and they're linearly independent over this ring. So again, the process terminated quickly. So after that, all the syzygies are 0. So in his famous 1890 paper, Hilbert showed that if you have capital N variables, you take modules of syzygies minimally. So you take generators, but no redundant ones, just minimal sets of generators. And he actually worked on the graded case. And this ends after at most n-1 steps if you start with vectors in a free module. Now, there are also modules that aren't free, which I'll talk about only very, very briefly. The least number of steps is called the projective dimension of the module spanned by the vectors. And you can consider quotients of a free module by a submodule, and then the bound goes up by 1. The bound for the quotient is 1 more than the bound for n. And I say that mainly, we'll be mostly looking at R mod I, where I is an ideal. And so sometimes people are worried about what happens when you start with R mod I, and sometimes when you start with I and it's just 1 different. So it doesn't make a big difference. So there's been a great deal of research recently on this problem. Suppose you have n homogeneous polynomials of degree at most d, like 4 quadratic polynomials or 3 cubic polynomials, something very specific. So is there a bound that depends only on n and d? So you don't know anything about the number of variables for the number of steps needed before the process of taking syzygies terminates. So this is quite different from what Hilbert did. Hilbert's bound was basically the number of variables or the number of variables minus 1. But here we have no idea. The number of variables might be Googleplex or some other very big number. And you want to get a bound just knowing that the degrees are small and that the number of polynomials is small or relatively small, but you know nothing about the variables. And if there is a bound, what is the best bound? Unfortunately, my allergies are acting up, so talking, I didn't realize this, makes me cough. So this question is due to Michael Stillman. And for linear forms, which you might as well think of as variables, this has been understood for a long time. You get very simple relations called Kazul relations, and I'm not going to talk about that case. And the case of 2 forms is easy. In the case of 3 quadratic forms, for quadratic forms, it's not difficult. And so far as I know, it was first solved in a conversation between David Eisenbud and Craig Hunicke, but not written up. After that, it gets hard. Okay, so if you're talking about 4 quadratic forms or 3 cubics, it's already very hard to figure out the answer. It doesn't take long for it to get hard. Oops, I accidentally hit the wrong thing. So for 4 quadratic forms, but only recently, the answer is known to be 5, but it's stated as 6 because it's stated for the quotient rather than for the ideal. And this is proved by Hunicke, Montero, McCullough, and Siciliano in 2018. The paper appeared only 2 years ago. And By the way, I can make these slides available, and I've given a handful of references. There are a huge number of references, but I've only given a handful on the slides. And then for 3 cubics, there was first a bound of 36 for R mod I by Engeda, and later Montero and McCullough showed that the best possible bound is 5. It's quite a, for a while it wasn't known, it was known to be between 36 and 5, and nobody knew which. What I want to mainly talk about today is proving that there is a bound that depends only on n and d, and in the general case, so this, in some sense, it solves the question completely in terms of existence. There really is a bound that depends only on n and d. Unfortunately, it's nowhere near the best bound. So, but at least we know there's a bound, and I'm going to talk about how that was done. So this is work with, joint work with Tigran Ananyan, and the work itself raises many more questions. So here's the theorem. The projective dimension of the ideal generated by at most n forms of degree at most d. So again, this is in some polynomial ring over a field. It doesn't matter whether the field is algebraically closed here, because replacing it with the algebraic closure does not change the projective dimensions. So, but as say, I'm not going to worry about that point. Has a bound, which I'm calling CND. It's independent of the number of variables and of the base field. So it doesn't, Stillman's original question was rather vague as far as the field went, but it turns out when we get specific bounds, we can do a little better if the characteristic is big or 0, if it's, which we can think of as sort of infinite characteristic. And some of our results on low degree are different in characteristic 2 and characteristic 3, but there's always a bound. And this theorem asserts that. And I want to explain why this is true, at least something about why it's true. And the idea of the proof is to take the forms that you're given, and they may have lots of relations that you don't want, and therefore complicated syzygies, and put them into a polynomial ring in fewer variables. And then that small number of variables gives you a bound. If it depends only on n and d, and not on the capital N, the big number of variables. So the idea is you can put the forms into a polynomial ring in fewer variables. But they can't just be algebraically dependent. You need to prove something very good about these new variables, so to speak. And I'll talk about what very good means in this context. So the number of the variables in the smaller polynomial ring is bounded in terms of the same n and d as above. It depends only on the number of forms and their degrees. And it's independent of the number of variables n. And there seems to be an extra parenthesis, but I guess that won't confuse anybody. So I want to review a little bit of algebraic geometry. So I'm only going to be talking about algebraic geometry in Kn. I'm not using any projective geometry. So, and the word projective dimension, it doesn't have to do with projective geometry. Projective is an weakening of free module. So that's why that word is used. So this is all in Kn. And so the points defined by polynomials, that's called a closed algebraic set. And if it's not a union of two proper closed subsets, it's called irreducible or a variety. and every closed algebraic set's a finite union of mutually incomparable varieties. So varieties are the main thing. In a way, the algebraic sets correspond to the ideals generated by the polynomials. The varieties correspond to the smallest prime ideals containing them. And algebraic sets have a dimension, which can be characterized in many ways. So one of them is that there's a map expressible using only polynomials in the coordinates onto KD. That means dimension D, that has finite fibers. And that pretty much, that corresponds with geometric intuition, I hope. I mean, when the field is the complex numbers, this will be, these things are topological spaces in the ordinary Euclidean sense, and this dimension will be half the real dimension. So the complex numbers themselves would have dimension 1. Now from here on, I'm going to talk only about homogeneous polynomials. So our algebraic sets will be defined by homogeneous polynomials. And that means I could talk about projector space, but I don't need to, so I'm keeping it as simple as possible. And then the dimension of X is the same as n minus h, where h is the largest dimension of a vector subspace that meets X just at the origin. So it's the number, if you like, it's the number of hyperplanes you have to intersect with X until you cut the dimension down to 0. And this number h is called the codimension. So the dimension and the codimension add up to the number of variables, or the dimension of Kn. And over any field, just as over the complex numbers, you can talk about smooth points or non-singular points and singular points. In the case of a variety, the singular locus is defined by the vanishing of certain size minors of a Jacobian matrix. So the situation is the same as over the complex numbers. You can do the same thing over any algebraically closed field and get analogous notions. So in a polynomial ring over a field, any elements that are algebraically independent can be thought of as variables in a new polynomial ring contained in the original. But as I say, that's not good enough. This is the kind of thing we want to do, but algebraic independence is very far from being enough. It's, I say, not enough. By the way, red statements are kind of cautionary, while green statements mean go for it. To some extent, I wasn't absolutely consistent in picking colors for this, although it was a lot of fun. So, so we only want to use what's called a regular sequence of forms, and they will be algebraically independent, but this regularity is a much, much stronger condition. So these are going to be homogeneous elements of positive degree. And in a polynomial ring over an algebraically closed field, they have many characterizations, and I'm going to give you a bunch of them. So if we have G1 through GH in the polynomial ring, these are homogeneous. Then the following conditions are equivalent. So first, the dimension of the algebraic set where they all vanish is n minus h. So you have h of them. It means that every time you impose a new condition, you cut the dimension of the vanishing set down by 1. By the way, the regular sequence is used with a different general meaning in commutative algebra, but this is equivalent in the polynomial ring case. And that's because polynomial rings are Cohn-Macaulay rings, which I'm not going to talk about, but I'll mention it. So the codimension of the algebraic set where they all vanish is h. Remember, there are h elements in this sequence. And so another characterization is that these g's can be extended to a sequence of homogeneous polynomials, g1 through gn, that vanish only at the origin. And this is just a bigger regular sequence, maximal one. Well, now we've cut the dimension down to 0, so the codimension is n. So a third condition that's equivalent is they can be extended to G. Oh, these F's should have been G's. Sorry, there are no F's. These F1 through Fn should have been G1 through Gn. And the fourth condition is, so here notice not only are these GFs, so to speak, there are n of them, but R is a finitely generated free module over this smaller polynomial ring they generate. And that turns out to imply that R is a free module over the original K of G1 through GH. So as a module over the smaller ring, it's just a direct sum of many copies of it. And I'm mentioning the fifth condition, but I'm not going to refer to it again. And it says that each of them is not a zero divisor on the quotient ring by its predecessors. And I mention it because in the general case in commutative algebra, that's how regular sequences are defined. Plus, they shouldn't generate the unit ideal. Here, that's not an issue because everything's homogeneous with positive degree. So I mentioned condition 5 just to make the connection with the standard definition, but I'm not going to use it for anything. In fact, really the only thing I want to use from now on about regular sequences is pretty much condition 4, that this is saying this fact that R is free over the polynomial ring and the G's means that the transition is very good between them as far as syzygies go. And these conditions do imply algebraic independence, but they're much, much stronger. So by way of example, if you have variables or powers of distinct variables, that's a regular sequence. And here's a less simple example, but this is also a regular sequence. These are homogeneous of degrees 17, 19, and 29. Harder to see that it's true. But if you want something that's not a regular sequence, look at x1, x2, and x1, x3 in the polynomial ring and 3 variables. And you could do the same thing in capital N variables. They're algebraically independent because x2 and x3 are. So in that sense, they're usable as variables. However, the algebraic set they determine has codimension 1 and not 2. They don't cut the dimension down. In fact, they don't even do as good a job of cutting things down as x1 by itself. So likewise, if you take the minors of a 2x3 matrix, this is a little more interesting. Those are algebraically independent, those deltas, but they're not a regular sequence. And there are 3 of them, but the algebraic set defined by their vanishing has codimension 2, not 3. So the main thing we want to make use of is that if you have a regular sequence of forms in here, I'm sorry, I forgot the backslash. That free is supposed to be green. And this means you can compute the syzygies over the smaller ring, and then just they'll work over the bigger ring. The generators work, and even repeatedly. So in the presence of freeness, the relations in S on vectors in R are generated as an S module by the relations over R. So you don't have to worry about S at all. You can work with a smaller polynomial ring. And this works for iterated modules of syzygies as well. So getting to a smaller polynomial, let's go back for a second. Getting to a smaller polynomial ring is the key to this proof. That implies the theorem. And you get a bound from this of capital C from this bound of capital B that I've been talking about. So this theorem, this is the main theorem of the paper. This is in the Journal of the AMS. It appeared last year. So, so we thought about this for 7 years before seeing how to do it. So suppose you have n forms of degree at most d, and then there's an integer that doesn't depend on the number of variables, which I haven't mentioned, and nor on the field, and a regular sequence of forms whose length is b, given by this bound. And these new forms have, the degree doesn't go up. You don't need to increase the degree. And the polynomial ring in the F's is contained, all the F's are contained in this polynomial ring generated by the new elements G1 through GB. And that means that the projective dimension of the span of any vectors with, that should be entries, not entires, sorry. Entries in K of F1 through Fn is at most B minus 1. Or if you divide out by the ideal, you would say B. So, so we get this bound, and it's much larger than the bound you need for projective dimension, because we know from specific examples that you can do much better in lots of examples. And so there are lots of conjectures about what the best bound is, but really only progress in very few cases about that. So for n quadratic forms, there's a conjectured bound of h times n minus h plus 1 minus 1. The minus 1 is for the forms themselves, not instead of the ideal, instead of R mod I. And here h is the codimension of the algebraic set defined by the forms. H is at most n. So if you want to see what the biggest value this can have, it's about a half. You want to take h to be about a half of n, or a half of n plus 1. So, so this bound is quadratic in n. It's roughly, it's asymptotic to 1/2 n squared. And you can't do any better than this by examples of McCulloch. And but what do we get for Bn2 for n quadratic forms by our methods? Well, d equals 2, and we get this bound. So it's already exponential. So our bound for, now I don't know if there's a lot better, something you can do that's a lot better for the B, but for the projective dimension, for the projective dimension, it looks really bad. Still, it's a bound. And in a more recent paper, we gave bounds of a sort when d is at most 4. When d equals 4, we had to exclude characteristic 2 and 3 because we use somewhat different methods to get bounds. However, the bound for n cubics is n-fold exponential, like n to the n to the n, except it's worse than that because some of those are like n squared in there. And the bound for n quartics is much worse. I'll say a little bit about it. So, so these bounds are horrendously big, and I hope one can do much better, but nobody knows how yet. By the way, a lot of other people are working on giving new proofs, but they seem to be mostly less constructive than our proof, using ultra products or polynomial rings in infinitely many variables. And some of them are kind of quick, but they're not constructive, as far as I know. So one of the key ideas that underlies the proof of the main theorem is the notion of strength. So I want to talk about the notion of strength. And I want to talk about strength of a form and also for a vector space spanned by forms. So if you have a form of degree 2 or more, we say that it has a K collapse if it's an ideal generated by K or fewer forms of strictly lower positive degree. So you can write it as a sum of multiples of lower degree forms and use only K of them. So F has an expression like this, where the G's and the H's in this will all have positive degree smaller than the degree of F. And we call a form that has no K collapse K strong. We say its strength is at least K. So this is a relatively new notion, and it came up in several different contexts. A number of people started thinking about it at around the same time. So the strength of a form is the greatest integer such that it's K strong. Of course, it'll always collapse if you use the number, take K to be the number of variables. You can write it as a sum of multiples of things of degree 1. But the interesting case is where K is much smaller than the number of variables. Now, 1 forms can never be written in terms of things of lower degree. So we define the strength to be plus infinity. They have no collapse. So 1 collapse means reducible. You can write it as FG1H1. So if the strength is 1, then the polynomial is irreducible. That's the meaning of strength 1. So you can think of K strong for large K as being super irreducible, if you like. Irreducibility gone wild. Okay. Now, the notion of strength becomes even more useful. I'm tempted to say stronger, but I'll just say even more useful when you apply it to all the elements in a vector space of forms of the same degree. So we say that a vector space of forms is K strong if the non-zero elements are K strong. So none of them has a K collapse. And that means taking not just the basis, but all the linear combinations of the basis elements. So you have to look at everything that's non-zero in the vector space. So this condition is imposed element-wise. It's a condition on each element, each non-zero element anyway. So x1, x2 is not 1 strong. It's not irreducible. But if you add x3 squared, it is. It is 1 strong. And if you look at this quadratic form, it is 2 strong. You can't put it into an ideal generated by 2 linear forms, but it has a 3 collapse because you could put it into x1, x3, x5, for example. And if you take n linear combinations of K variables and use indeterminate coefficients, then you get a vector space of forms that are K strong, but not K plus 1 strong. So, so there's a really critical intermediate theorem about strength that's one of the key tools in the proof of this theorem. And so this is a new function that I'm talking about of n and d only, no reference to the field, no reference to the number of variables. And what this function does is if you have a vector space of dimension n as a vector space in a polynomial ring, and the elements are degree d, the non-zero elements. So you've got something like n polynomials of degree d, and you're looking at all linear combinations of them. if the strength of that vector space is this big, now this is bounded compared to capital N, but it's in practice, it still might be a very big number. But if you have enough strength, then any sequence of linearly independents in V is a regular sequence. So we call A of ND a strength function. And the moral here is great strength implies regular sequence. And as we go along, I'll give some examples of these strength functions. So turns out the existence of A and D implies an affirmative answer to the theorem. The fact that you can having great strength forces these bounds on where you can put the original forms into a smaller but very good polynomial ring comes out of this strength theorem. So strength is a very central notion in this study. And of course, BND gives CND, the bound on projective dimension. So you go from A to B to C here by coincidence. And I want to get across something about the idea of why the existence of A and D helps you. So I want to focus on a simplest case, and the first one that Tigran and I thought about, where you have linear forms and quadrics. So you have a sequence of n linear and quadric forms that are linearly independent. And assume that no non-trivial linear, the combination of the quadrics is generated by, it's in an ideal generated by AN2 linear forms. So there's no AN2 collapse. This is the level of strength we needed. And then the quadrics form a regular sequence. And this gives you a bound. But on the other hand, if a quadric collapses, then you can write it in terms of linear forms, and you know what A is. So what happens is you put these linear forms into your family. And of course, you now have a lot more forms, because A might be pretty big, but the number of quadrics went down one. So you gained something with the degrees. The number of quadrics didn't actually went down one, even though the number of linear forms increased by a controlled amount, but the number of quadrics, the worst degree that you're worried about, went down one. So in a certain sense, degree has gone down, only on one of them, but at the cost of increasing the number of forms of lower degree. But you can repeat this argument until you either get a regular sequence or there are no quadrics left. So with each collapse, the number of forms increases, the number of linear forms, while the number of quadratic forms decreases. But the total number that you have can be kept under control. You can track it. So from the values of A and D, one can recursively calculate a value of B and D. So at every stage, the algebra generated by the new forms contains the algebra generated by the previous sequence of forms. So you are capturing the original forms. So strength yields regular sequences, while in a suitable sense, collapse allows one to decrease the degrees, at least one of the worst ones. And this is enough to get a recursion going in general. But to prove the theorem, I just want to keep track of the time, you have to do a lot more. Uh, and of course, I'm going to hide most of the details, which nobody would ever want to see in a talk. Uh, but you have to create strength functions, not just for one vector space, but for sum of vector spaces where each of them has a degree. All the elements are of the same degree. But once you can do it for one vector space, we have tricks for getting a sum of vector spaces, a strength function that works for all of them. There's an interesting theorem involved, but we can do that. And unfortunately, and this is a little bit technical, you need to prove something stronger about the strength functions. They need to do more for you than give regular sequences. Regular sequences are great, but we want something better than a regular sequence to make the proof, to make the induction work. You've got to do better and better stuff in lower degree to get the next step to work in high degree. So I want to tell you about what you need to get that's beyond regular sequence. So I'm going to fix a positive integer eta. Suppose you have vector space of very great strength, but it's still small. It only depends on little n and little d. That's what I think of as small. It doesn't depend on the number of variables. Then one wants to be able to conclude that the quotients of the polynomial ring by ideals generated by linearly independent subsets of V, you want them to be regular sequences. I've already said you can get strength functions that do that, but you also want to control the singular locus so that it has codimension at least eta plus 1, whatever eta is. So we're not controlling the codimension of the singular locus initially. So as eta goes up, these varieties you get by killing the regular sequences have better and better singularities. The singular locus is getting smaller in some weird sense. Well, this sense. So this is a bit technical. So you can do it using larger strength functions. So we stick an eta in when we're worrying about this codimension. And there's still no dependence on n or the field for these refined high-tech strength functions where we've put an eta in. And once eta is at least 1, the codimension condition makes the quotients domains. And if you know what a normal domain is, it even makes them normal. So they have better singularities. When eta is at least 3, you get that they're UFDs, they're unique factorization domains. And this is saying when you have that large strength, when you kill any subset of independent elements in this vector space, the quotient is a variety, and the ring you get is unique factorization. And this already when eta is 1, you're getting integral domains, no matter which elements you kill in the sequence. So I'm going to say just a little bit more about how eta comes into the proof. This thing about UFD is using a theorem of Grothendieck, originally conjectured by Samuel, about when a complete intersection is a UFD. And to make the proof work, we need to get these results for all eta, because you keep, as you go up in degree, to make things work in the next degree, you need a larger eta in the smaller degrees. And once eta is at least 1, I said all the ideals generated by elements in the regular sequence are prime. Their quotient by them is an integral domain. But in fact, something much, much stronger is true once you have that condition. It turns out that every ideal in the small ring expands to a prime ideal, every prime ideal in the small ring expands to a prime ideal in the original ring. And that enables you to compare something called primary decomposition. So I'm not going to talk in detail about that, but it is essential in the proof to do that, to keep track. You can, once you have this machinery going, you can control many, many invariants of ideals, not just projective dimension. So part of the argument involves forcing regular sequence into the ideals generated by minors of Jacobian matrices. And that's how we control the codimension of the singular locus. And it's a key point that the entries of the Jacobian have smaller degree than the original polynomials. So you're doing something there in smaller degree. It's still very complicated. And this guarantees a suitably high codimension in the relevant singular loci. So that's what the regular sequence business is key, but you can push it and get more information out of it than you thought you might. And you can and need to give more bounds, like the degrees and numbers of minimal generators of the smallest primes containing your regular sequence, or some family of polynomials, whether it's regular or not. And you can do that by pushing them into a smaller polynomial ring generated by a very good regular sequence, where primes expand to primes. So you can, so if you know about primary decomposition, you get bounds independent of capital N for everything about at least one primary decomposition. You know bounds on the degrees of the generators of the ideals occurring and the numbers of generators and how many there are. Everything is bounded, provided you're starting with a known number of forms of degree at most D. So the complete argument involves formulating 5 theorems bounding behavior independent of N, and proving them all by a simultaneous intertwined induction, where you use the fact that you know everything in lower degree to get everything in the next degree. And the induction takes place not over the integers, but over a well-ordered set. And that it's similar to the ordered set for if you're studying homogeneous lexicographic order on monomials. That's a well-ordered set. This one is really isomorphic to it, the one you use in these proofs. And whenever you have the strength functions for a single degree up to D, you get the strength functions for vector spaces involving forms of several degrees. And recursively, you can then get values of B. So these A functions determine the capital B functions, which of course then can be used for capital C. Okay, so I want to talk a little bit about what we know about the existence of these strength functions. And I'm not going to be able to give any detail about proofs, of course, but they're really, for quadrics, it's really nice. So if every element is n minus, so you have a n quadrics. If every element is n minus 1 strong, then every sequence of linearly independent elements in the vector space is a regular sequence. So the strength function for dimension n is only n minus 1. And you may want to know what happens if you bring eta into it. And you just have to add this eta over 2 rounded up to get eta into it. So eta is not a big deal in these strength functions. So that's the result for quadrics, and that is best possible. Whoa, I meant to put in more pauses, but okay. So, so if you have this much strength, n minus 1 plus eta over 2 rounded up, you not only get quotients, you get regular sequence in which the singular locus has codimension at least eta plus 1. So in terms of A, I said this without using A. In terms of A, it says A of n2 is n minus 1, and eta A of n2 is this function that I have in the statement of the theorem. But this rather small strength function, when you go to B, leads to exponential results. And when D equals 3, things are also not too bad. We want a strength function for cubics, and the one we have is at worst 16 times n plus eta squared. So if there's no eta, just 16n squared. And in fact, we only need 16 in characteristic 2. We can use 8 in any other characteristic. Although the results in the paper are more precise and give more complicated formulas, but that's not worth doing in this talk. But that leads to values for B that are n-fold exponential. So even this quadratic strength function leads to terrible values for B. And how am I doing on time? Oh, I have 4 whole minutes. Okay. So now we have a linear bound that works for strength with quadrics and a quadratic bound that works for strength with cubics. And I'm sure you're all ready to conjecture that there should be a cubic bound that works for strength with quartics. I was, and I still am, and I think there is. I'll conjecture it. However, that's not what we got. We can't prove anything like that, but we did compute a strength bound that works for quartics. However, we had to throw out characteristic 2 and characteristic 3 because we use Euler's formula in the proof. The proofs for quartics are different from the general proof. So if D equals 4 and the characteristic is not 2 or 3, then the strength function is asymptotic to this thing. That's the strength function. What we're hoping for is n to the 4th. K is 2n plus eta. So I wrote it this way. It's easier to read this way. So, so the best thing we could do with strength in degree 4 is already exponential in n in a fairly horrible way. By the way, this is not what's in the paper has more precise statements, not this one. I sort of rounded up a bit to get something simpler. So that's the situation with strength. I think there should be a cubic function, but the result for Bn4, now with just n a quadratic thing there, we got n-fold exponentiation. So there is a bound for Bn4, which is beyond description as far as I'm concerned when you use this strength function. But it exists, and I say the bounds exist in general. So this leads me to questions. What is the best possible bound for projected dimension given n polynomials of degree d? And for d equals 2, the conjecture on the bound is this n times n minus h plus 1. That's for r mod I. I didn't subtract 1 there. And h is the height. And this is, at worst, something like a half n squared asymptotically. And it's the codimension, not the co-dimension, but okay. And so it's possible, so far as I know, that for n forms of degree d, there's a bound of the form some constant times n to the d. But let's say that's totally unknown even for cubics. And what about the strength functions? Well, it's possible that one can use a constant times n to the d minus 1. That works for quadrics and cubics. And we can ask for what is the best or smallest value for B and D, and that's totally not known. So I'll finish with this question. Oh, I didn't realize that I'm going off the bottom here. So given n quadratic forms, our results tell us that there's the highest possible degree for a minimal generator of a minimal prime. And the worst example that I know of is take the entries of an n by n matrix of determinants multiplied by an n by 1 column. And then in one of the minimal primes, you get the determinant of the n by n matrix. So you can get a degree n minimal generator. So with n quadratic forms, you can get a minimal generator of degree n in one of the minimal primes. I don't know anything worse, but I don't know any really good theorems about this. So this is a very simple question about quadratic forms. Given n quadratic forms, given a minimal prime, and looking at the minimal generators, how big a degree do you need? There is a bound. It does not depend on the field or the number of variables. Just little n, some function. And it might be little n, the degree bound, I don't know. So this is just an example of another open question. I apologize that this was a little too long. And thanks for listening.
Well, thank you, Mel. Thanks a lot for the wonderful talk. Are there any questions? If you have a question, you can mute your Zoom and then say it if you want to.
Maybe I'll stop the screen sharing and open chat.
Okay. Yeah, I have been monitoring it, so it doesn't have questions yet.
People can speak.
Yeah, but in the meantime, will people start thinking about questions, or will start muting? I have a couple. First one, I guess from you mentioned that there are several invariants that can be bounded from your methods, not only the projective dimension. I assume one of them is the Castelnuovo-Mumford regularity.
Yes, and in fact, that was proved before it was shown to be equivalent by Caviglia. Prior to knowing that they were both bounded.
So really then my question is, because if you can get a direct bound from your methods from the Castelnuovo regularity, and you can get a direct bound for projective dimension, and then apply Caviglia operation, how these two compare? Either directly from your methods is better?
Well, I mean, he proved that a bound for one implies a bound for the other, but I don't know how effective those numbers are offhand. But I'm sure you can find his paper easily. Mm-hmm. I don't. We're kind of focused on projected dimension because, but I could have raised the same questions for Castelnuovo-Mumford regularity. And there, I don't know what the best answers known are. The papers have focused on projected dimension.
Okay.
And I think the regularity bounds are bigger.
Okay.
So I'm not sure it's helping with the projected dimension.
And another question, which is not that I mean, it's close but not that related. So is it any hope that if you give you n forms of the grid D, you can tell me something about the size of a Grobner basis using your methods? Like, the Grobner basis is not going to have a degree at most something, or like size at most something.
I don't think that a bound on that is known that independent of the number of variables. Okay. I don't think our methods yield that.
Okay.
I may be, a lot of other people, so Snowden and Ehrman and Stephen Sam and Jan Drazma, there are a whole bunch of people writing papers about this now. And also Kazhdan. And so the literature is growing very fast. And also people are studying questions about strength, like what is the strength of a generic form of a given degree? Things like that are open. I could have listed a lot more open questions. And there is a direct question about, given a level of strength for just one form, just take one polynomial of a certain degree, and given a level of strength, what is the most you can say about the codimension of the singular locus?
Okay.
Just for one. And people are proving things about that. But the Grosvenor basis thing, the bounds I know involve knowing the number of variables. And putting them in a smaller polynomial ring doesn't solve the problem.
Okay.
So here's something that Tigran and I did in a separate paper, which I haven't talked about today. We took just two quadratic forms, okay? And now for each number of variables, a regular sequence, two quadratic forms in a regular sequence. Now for each number of variables, there's a Lex ideal that has the same Hilbert function up to, and as you increase the number of variables, what happens in any given degree stabilizes in terms of the number of generators of that approximating Lex ideal. But so you can ask, how do those numbers behave? And they're double exponential.
Oh.
So the paper's on my webpage and on the archive, if you're interested. It's called something like universal Lex ideals and Hamilton numbers. So the numbers that come up were studied by Hamilton in a different context a couple hundred years ago. Had to do with the number of Chernhausen-like transformations you needed to do to simplify a polynomial equation and trying to solve it by radicals. So they came up before, but nobody seems to have done anything with them recently. We came up with the same numbers and counting numbers of generators of these approximating lexicographic ideals. That's a bad sign in terms of, possibly a bad sign in terms of behavior of Grosvenor bases as you increase the number of variables.
Okay, well, thanks,
but
Mel.
I'm not sure, you know, there are a lot of papers now, it's hard to track them all.
Is there any other question for Mel? You can either unmute yourself.
If you think of one, feel free to email me, anybody. And as I say, I'm gonna, the slides are of course in a Beamer file. I'm gonna put them into a more manageable kind of tech file. And I'll put them up on my webpage and I'll email the PDF file to you also, Luis.
Okay, thank you.
If anybody wants to look at them.